Welcome back to geometry. Today we're going to get ourselves started on chapter 12. And what we're doing here is we're moving from two-dimensional shapes that we've been focusing on for the vast majority of the year to three-dimensional shapes. And the term that we use just in general for three-dimensional shapes is solids. All right? Now we'll start with a couple of definitions just to get ourselves going a bit here. We've got four definitions. First, polyhedron. All right, polyhedron is a three-dimensional solid bounded by polygons. And what we mean by bounded, when we say the word bounded there, bounded just means that the outside shapes that make up the solid will be polygons. Now remember, a polygon is, we've had that definition now for a long time, is just, excuse me, is just going to be a two-dimensional shape that's formed by line segments. So we have straight line segments that make up a polygon. Okay? Now some of the other definitions that go along with the polyhedron are face, edge, and vertex. And the definitions, as you can see on the screen, face is one of the polygons, meaning one of the polygons that makes up the polyhedron. Edge is the intersection of two faces. So where two faces come together, that's called an edge. And vertex is a point where three or more edges meet. Okay? So feel free to get those definitions down when you have the chance. Pause the video if you need to. And then what I've got here is just some pictures that I've taken. And my question to everybody is the three-dimensional shape that you see a polyhedron or not? All right, so it's just yes/no questions. Would the shape that you're looking at be a polyhedron? Would the box be a polyhedron? Would the cylinder, would the cone, would this prism, would this shape be a polyhedron, yes or no? Well, how about my number one? How about just the box, the rectangular solid? Would that be a polyhedron? Yes, it's three-dimensional, and all of its surfaces are polygons. We have a rectangle here as an example. We'd have a rectangle here as an example. All of the sides are rectangles, so this is going to be a yes. Would the cylinder be a polyhedron? No. And it's going to be a no because the end of this polyhedron is a circle, and a circle is not defined to be a polygon, so this would be a no. Therefore, number three is probably an easy one. Yes or no there? No, because the top of this cone, again, is a circle, and a circle is not a polygon. How about the prism shown down below? I guess I forgot to number this. This would have been number 4. Is that number 4 going to be a polyhedron? Yes, because no matter what side you look at, if you look at the front, that's a triangle. If you were to look at this side coming down this way, this is a rectangle, it appears to be. So all of the sides would be polygons, so this would be a yes. And how about my number 5? We don't really have a great name for that, but would that be polyhedron? Yes. No matter what side you look at, it's going to be a polygon. The top would be a pentagon. This side, as an example, would be a rectangle. The bottom would be a pentagon. So all of the sides that make this up, they're technically called faces, would be polygons. So this would be yes. Okay? Alrighty. Now, a couple more definitions. The first one, prism. And a prism is defined to be a three-dimensional solid where opposite faces, and the opposite faces are usually called bases, are congruent. And then, so that's the first one. And then the second one's called a pyramid, and that's a three-dimensional solid where 3 or more edges come to a point without a face. Okay, and let me just kind of show you. I've got a couple of examples down below. This one over to the left is going to be a prism because the opposite faces are congruent to each other. So if you were to look at the top and the bottom, those are going to be, if those are congruent, then we're going to call that a prism. Now, kind of the neat thing about some shapes is you can actually call different pairs of faces the bases. In a box like this, you could have also called the left-hand side here and the right-hand side, you could have called those the bases because they would have been congruent as well. And then a pyramid is when we have a solid where 3 or more of the edges, in this case would be 4 edges, come to a point without a face. So this edge comes up to this point, this edge comes up to this point, this edge comes up this edge. All of these edges come up to a point that doesn't have a face attached. So that's called a pyramid. Okay? All right. And then what I'm going to ask you to practice, just to kind of start to get the hang of polyhedron, is I'm going to ask you to count the number of faces, the number of edges, and the number of vertices that a polyhedron might have. Okay, so as an example in my number 1, how many faces would this shape have? All right, take a look. All right, this is going to have 5 faces. The idea is that we have what appears to either be a square or a rectangle as a base, a bottom, and then we have 4 triangles that all come up to this point. So we have one 4-sided base and then 4 triangles that come up to meet at the point. So there'd be 5 faces. Okay? Now the number of edges I can help you out with by actually drawing them in. I could draw lines that represent all of the edges. So we could just do them as I draw them, I'll count. So 1, 2, 3, 4, 5, 6, 7, and 8. So there's 8 edges in this pyramid. And then vertices are where 3 or more of the edges come together, and I better switch colors so it's easier to see them. So vertices are going to be where all these edges come together, so we're going to have 1, 2, 3, 4, 5 vertices. 5 vertices. Okay? So we're just going to bob through a couple more of these just to try and get you a feel for it. So again, I'm going to ask you to count faces, edges, and vertices. And if you guys want to do it on your own, you could just pause the video, run through what you think is the number of faces, edges, and vertices, and then start the video again and see if it matches up to what I have. Okay? All right, so faces here. Let me choose my laser pointer. What we're going to have is a triangular front, a triangular back, and then 3 what look like rectangles that make up the sides that kind of connect the triangles together. So it'd be triangle on the front, triangle on the back, and then 3 rectangles for a total of 5 faces. And then the edges, again, I could actually draw out for you. So 1, 2, 3, 4 that make up the bottom. And then 5, 6, 7, 8, and do you guys see the last one? 9. So there's going to be 9 edges. 9 edges. And then the number of vertices, again, I'll color these in blue. So 1, 2, 3, 4 around the bottom, 4 around the bottom, and then 5 and 6. Okay, everyone's starting to get the hang of that a little bit. I've got a couple that are just a little bit more complicated that we can run through. Let's see, I'm going to pick red again just so they're the same. Let's see, can you guys count faces? What did I do second? Edges, I think I did. And vertices. And while I'm at it, I'm just going to write that out twice. Faces, edges and vertices. Okay, so how about faces on the number 3 example? Okay, well, what we're going to have is a pentagon for the top, pentagon for the bottom, so that would be pentagon on the top, 1, pentagon on the bottom, 2, and because a pentagon has 5 sides, we'd have a rectangle kind of going down the back, down the left-hand side, coming down the front, right-hand side, and then right hand in the back. So there'd be 5 rectangles kind of moving vertically, moving up and down there. So 5 around plus the 2, the top and the bottom, would make a total of, oops, pick my pencil, 7 faces. Okay, the edges are a little bit easier this time. We have a pentagon on the bottom, so that's 5. A pentagon on the top, so that's 5. And then we're going to have 5 edges that connect the top and the bottom. So 5 around the bottom, 5 around the top, and then 5 that connects the sides. So altogether that is going to be 15. And then the number of vertices, because we have 5 edges, we'd have 5 vertices around the bottom and 5 vertices around the top for a total of 10. Okay? And then finally, how about this last shape? How many faces? Well, we have kind of a left-hand side over here, that has 1, 2, 3, 4, 5, 6 edges to it, 6 sides. Okay, and then we have that same shape over here, that same hexagon over here. But because the ends are hexagons, that means there's going to be 6 rectangles that connect the hexagon on the front to the hexagon on the back. So 1, 2, and then 6 rectangles that connect. So that's going to be a total of 8. The number of edges then would be the 6 edges that make up the hexagon on this side, the 6 on the back side, and then the 6 lines that would connect the front to the back. So 6, 6, and 6 makes a total of 18. And then the vertices, since the front here has 6 sides, it would then have 6 vertices. Well, that means the back has to have 6 vertices. All right. Oops, I actually put in an extra one where I didn't need one. There we go. There we go. So 6 in the front, 6 in the back makes a total of 12. All right, looking okay with everybody? So I'll ask you guys to try that on your own a little bit to see how it works. All right, see how well that works. Okay, next we're going to look at the only theorem in this section. There's just one, right? And it's numbered 12.1. And it's called Euler's theorem, named after a famous mathematician. And what it simply says is, and I forgot to write this out, so let me put it off to the side. In any polyhedron, the number of faces plus the number of vertices equals 2 plus the number of edges. So the number of faces that a polyhedron has plus the number of vertices that a polyhedron has is always going to be equal to 2 plus the number of edges. Or if you'd rather abbreviate it, I kind of like the abbreviated form. F plus V is always equal to 2 plus E. F for faces, V for vertices, E for edges. So if I just simply give you some numerical problems and I say, well, if I tell you guys there's 4 vertices and 6 edges, can you tell me how many faces? Well, what I would expect you to do is just simply take the equation, F plus V equals 2 plus E, and replace what values you know. Here I know the number of vertices is 4, and the number of edges is 6. Can you guys then find the number of faces? In other words, can you solve the equation? Well, of course you can. 2 plus 6 is 8. And when I move plus 4 to the other side by subtraction, that means I'd have to have 4 faces. And let me just jog through that same sort of thing a couple of times. If I tell you we have 10 faces and 24 edges, can you tell me how many vertices I'd have to have? Again, just starting with my equation, f plus v equals 2 plus e. The number of faces is 10. V is the one I'm looking for. I don't know that one. And the edges is 24. Again, can you guys solve? Sure. 2 plus 24 is 26. And when I move 10 to the other side by subtraction, 26 minus 10 is 16. And let's just jog through one more of those. This time I'm asking you for the edges, where I tell you that we have 14 faces and 24 vertices. Can you solve for E? Sure. 14 and 24 is 38. And then to move 2 to the other side, we'd have to subtract. So 38 minus 2 is 36. All right. So hopefully those problems will be fairly easy. And by the way, if you wanted to, you could go back to any of our shapes and confirm what we just did. All right, meaning I could give you a polyhedron like this one, ask you to count the faces, vertices, and edges, just like we were doing before, but then the extra thing I would ask you to do is check your numbers with Euler's theorem. So let's just jog through it. How about the faces on this box? Well, there's going to be a top, there's going to be a bottom, there's going to be a left side and a right side, and then there's going to be the front and the back. So altogether, there's going to be 6 faces. How many vertices would we have? Well, I've been doing those in blue, so I'll just keep that going. So vertices would be 1, 2, 3, 4, 5, 6, 7, 8. So there'd be 8 vertices. And then the edges I've been doing in red. So edges would be 1, 2, 3, 4 around the top, 5, 6, 7, 8 around the bottom. And then the 4 that connect vertically, so 9, 10, 11, and 12 edges. Okay? And then what Euler's theorem says is faces plus vertices equals 2 plus edges. And let's just confirm that works by replacing faces with 6, vertices with 8, and edges with 12. And when you do the arithmetic, 6 plus 8 is 14, 12 plus 2 is 14, so obviously that checks. You can see that Euler's theorem works on this shape. But if you prefer, you could go back to some of the problems we did earlier. Let me back up. So we could back up and check any of these problems with Euler's theorem to see that it actually is true. So that gives you kind of a way to confirm your faces, vertices, and edges that you've counted. Okay? All right. So just a couple other little things, and then we'll button up this video. A couple more definitions. First, a convex polyhedron and a concave polyhedron. Now, the definition for a convex is, it's convex if any 2 surface points can be connected by a segment that's either inside or on the polyhedron. And concave is really simple. If it's not convex, then it's got to be concave. So let me just give you some examples of that before we get to that third definition. If I give you some shapes like this, would these be considered convex or concave? Well, the idea is you pick any 2 points on the surface of the shape. So if I picked a point on the top of this cube, and then I picked a point on the front of the cube, and I connected those with a line segment, would that line segment have to be inside the cube? Is there any way to draw it outside? No. So this one is called convex. But if I pick a point on this next kind of crazy star-shaped thing, if I pick a point over here on this ledge where one arm of the star shape would be, if I pick a point on that ledge to the right, and then I pick a point maybe on this top, and if I connected those with a segment, would that be inside or outside of the star-shaped solid? It would be outside, so that one's going to be considered concave. And then this last shape, if I pick any point, maybe I'll pick a point on the front, and then maybe pick a point on this lower right. And if I connected those with a segment, would the segment have to be inside Yes, so that's considered convex. Okay, not real important, but pretty easy to make that determination. And then finally, the last thing for this section, the third definition in this little group, a regular polyhedron. And something's a regular polyhedron if and only if, remember, if and only if, all of the faces are regular polygons. And what does regular polygon mean? All of the sides are equal, all of the angles are equal. So things like squares are regular polygons. Equilateral triangles are regular polygons. Okay? But if we have a polyhedron where all of the faces are regular polygons, then it's called a regular polyhedron. And there's so few of these, they're very, very difficult to create. It turns out that there are 5. There's 5 common regular polyhedron. All right? And they're really hard to draw. They're really hard to draw. So what I did was I just took a picture of them out of your book. Okay? And I just showed you them. These are actually on page 796 if you want to get a better look at them in your textbook. But there's 5. There's what's called a regular tetrahedron that would have 4 faces, and each of the faces would be an equilateral triangle. The second one is a cube, which would have 6 faces. We're really familiar with that one, cubes. You know, when we roll dice, we're rolling cubes. Obviously, that means each one of the faces is then a square. We have a different type of one involving triangles. It's called a regular octahedron. Again, all of the shapes would be equilateral triangles, but we put 8 of them together. It has 8 faces. We put 8 of them together to form a regular octahedron. And then these last couple are pretty complicated. What we do on this fourth one is we create a regular dodecahedron that has 12 faces, and then every one of the shapes is a regular pentagon. Meaning all of the sides are equal, all of the angles are equal. All right, so you put 12 of those pentagons together, and we form a regular dodecahedron. And finally, the last one is called a regular icosahedron that has 20 faces. And again, please notice the shape is a triangle. So every one of the triangles then would be equilateral and, I guess, equiangular. Okay? So that's the end of section 1. So you should be able to stop this video and then open up your book and get yourself started in section 1. So have a good time. Let me know if you have any questions, and I hope you're having a good day. Talk to you soon.